Hello and welcome to the course Introduction to Advanced Cognitive Processes. I am Ark Verma from IIT Kanpur, and we have been talking about language in the last week or so. We've talked about aspects of reading in the last lecture, and I'll just try and take that discussion a little bit further by involving some of the cognitive processes that are there in reading, what are the aspects of scripts that you need to keep in mind, and a little bit about difficulties in reading, which is again covered under section referring to dyslexia. So let us begin rather quickly. So what kind of cognitive processes might be intervening reading? Written scripts differ. The script of Hindi or the script of English is very different from the script of Hebrew or Persian, or for that matter Chinese and Japanese. So different scripts have basically things called idiosyncratic features, and these idiosyncratic features are those unique aspects that each script has, and the reader of each of these scripts have to be well versed with, have to be familiarized with these idiosyncratic features in order to master reading using that particular script. Okay, so for example, alphabetic scripts are slightly different, pictographic scripts are different, and logographic scripts are different. So in an alphabetic script, typically English is an alphabetic script, there is a collection of letters. Each letters or groups of letters or bigrams and trigrams basically stand for or correspond to individual speech sounds or phonemes, and basically because each letter is a phoneme, you combine letters as you combine sounds and you create words out of that. A pictographic script is one, suppose for example Japanese, is wherein each character or symbol may look like the concepts that it is trying to convey. So for example, each letter, if you are say for example in a particular script, if you want to depict how you want to talk about a tree, it's quite probable that your description, that your symbol for tree looks or resembles the tree in some form. Okay, so that is one. And there are logographic scripts. In logographic scripts, what happens is that each symbol will map onto a unit of meaning, such as a morpheme or a word, and symbols don't really need to resemble what they are representing, unlike the pictographic scripts. So these are the three broad varieties of scripts that you can talk about. Now I have a very interesting example in Chinese. Chinese has been described by people as a morphosyllabic writing system. What is a morphosyllabic writing system? It's nothing really to be afraid of or very complicated. Here each symbol letter, each symbol will represent both a morpheme, a part of the word, and a syllable, a part of the phonological word. So characters consist of at least two elements. One is a semantic radical, which will tell you something about the meaning of what it is representing, and a phonological radical that will tell you about how this has to be pronounced. So in that sense, because there are morphemic and syllabic aspects, Chinese is referred to as a morphosyllabic scripts. However, there are some similarities with the morphological with the Chinese script with other scripts. For example, both kind of scripts will lead to automatic activation of phonological codes. So because there is the phonological radical, it will automatically help you generate a pronunciation for whatever you are reading. So heterophonic homographs, things that sound different but written in the same way. Suppose for example, wind has two sounds with the same font. So wind basically can be read as wind, or it can be read as wind. So it is a homograph which is the same set of words has two sounds associated with wind and wind. So these kind of things will take longer to read in both alphabetical scripts and scripts like Chinese. Also, words with inconsistent pronunciations will take a bit longer. Suppose HAVE is have, but SAV is not sav, it is save. So there is this inconsistency in pronunciation coming, which obviously will slow the reader down while reading aloud. Other thing are heterographic homophones. So things that are written differently but are sounding exactly the same. Meat takes longer to reject as food because MEET stands for meeting somebody, but it also sounds like MEAT, which is food. So if you kind of ask somebody, you present this word meat and ask them whether it's a food or not, it might take them a little bit longer to reject meat as a food item. Also, another effect, Pseudo homophones are difficult to reject, they take a longer time to reject. For example, the word brane, which basically resembles the sound of brain, brain, will take a little bit longer to reject. All of these kind of effects are very similarly happening across Chinese and scripts like English as well. So this is again some similarity between the two kinds of scripts. Now, because I was trying to talk about sounds and everything, let us talk a little bit about building block of reading. Okay, so learning to read, again I'm just borrowing a quote from Stein and Walsh from Traxler's book. Learning to read taxes our perceptual abilities to the limit far more than learning to talk, because again, if you remember, the way I began this discussion on reading is that reading is fairly unnatural. Okay, it requires finer visual, auditory, manual skills than almost anything that we learn. It's probably one of the most complicated tasks that we have to learn to master. Also, a sequence of small, minimally redundant visual symbols must be discriminated from each other and then translated into the phonemic sequence of sounds that comprise each word. So, I mean, this should help you kind of appreciate how difficult it is. These are very small symbols, A, B, C, D, E, F, or and those kind of things. These have to be converted into sounds. You are just looking at the visual. The visual has to be connected to the sound, and the sound has to be connected to the meaning. All of this has to be done at a fairly rapid pace in a rather dynamic fashion. So, in that sense, reading is difficult. So, what do you really need to do in order to learn to read? At least two things. When children are obtaining the knowledge that spoken words can be broken down into subparts, they are said to have phonemic awareness. So, something that the child has to learn to master is this aspect of phonemic awareness. Whatever I am saying can be broken down into sounds, and sounds have to be represented by basic symbols. So, this phonemic awareness that you can break things down into sounds is very important. The other thing is that children must realize that specific patterns of letters go with specific patterns of speech sounds. So, you have to be able to put letters together to create sounds, and that is also a very important effect. So, when they achieve this understanding of how sets of letters go together to create specific sounds, they are said to have grasped what is called the alphabetic principle. So, one of the two basic abilities that you need to master in order to learn to read is the phonemic awareness, the fact that spoken words can be broken down into subparts, smaller sounds, A, and the second is that these subparts can be created by putting together particular kinds of specific letters, is the alphabetic principle. These two things are very important. Phonemic awareness is supposed to be one of the most important precursors of literacy. Unless the child masters this principle of phonemic awareness, it is very difficult, rather impossible, for the child to master reading. It is thought to play a causal role in reading success because differences in phonemic awareness have been measured in children, and they have basically been correlated with their final ability to read. So, children who have been found to be very good with phonemic awareness have been found to acquire reading more seamlessly in a better way at earlier. Children who have been found to be deficient in phonemic awareness have been basically linked with difficulties in acquiring reading. Phonemic awareness, I mean, there is a way to measure them. Phonemic awareness can be accessed in a variety of ways. For example, the elision task, in which you give the child a particular sound. Suppose I ask the child to give cat, bat, mat, hat, and then I ask the child to say remove the k sound and tell me how it sounds. So, the child should be able to tell me at. Remove the b sound and how does this sound? The child should be able to tell me at. So, this is the elision task. A different kind of task is sound categorization, wherein basically it involves listening to sets of words and identifying the word that does not fit. Suppose I am saying pin, bun, fun, gun. So, the child should be able to tell that pin is different from bun, fun, and gun. Again, the idea is that you are teaching the child to appreciate how sounds are created, how sounds can be broken down and changed and manipulated, etc. In the blending task, again a very similar task to judge phonemic awareness, children hear an onset and a rhyme, the beginning of the syllable and the end of the syllable, and they basically try and see how what they will sound like if you are combining two different syllables. So, cap and pat. How do you if you take the beginning of one and end of one, it probably can be made as pap. So, the child needs to be able to break these things down and play with this a little bit, so that the child acquires phonemic awareness and masters the basic principle of reading. Now, children's composite scores on tests of phonemic awareness using tasks like I just described here have been found to be strongly correlated with the development of reading skills at a later point in time. Also, it has been seen that children who are less phonemically aware will experience greater difficulty in learning to read, and for this reason people have come up with various methods, various interventions to develop and enhance the children's phonemic awareness, and hence to increase the likelihood that they will turn into better readers, highly skilled readers as time passes by. So, this is a little bit about phonemic awareness. Let us now move to recognizing visual words. In the last lecture, I was talking to you about reading using eye movements. I was mostly talking a little bit about how do you read longer sentences. I am just in this lecture spending some time on reading individual words. So, individual word reading basically involves taking a perceptual input and using it to recognize a word and meaning. There are two kinds of models, dual root models and single root models. The dual root models basically have been one of the most investigated accounts of visual word recognition, and these models are called dual root or dual process models because they propose that at least there are two ways of wherein reading can occur. The first way is the direct access way, and the second way is the sounding out way. I will just describe this in a little bit more. So, the idea is if you are actually looking at a bunch of letters put together as a word, there are two ways that you can read it. The first is that you can use a sequence of letters to access a word's lexical entry by converting that sequence of letters into that of phoneme. Suppose you are reading B-A-T, bat. You have to come up with a sound of what B stands for and what A stands for and what T stands for, link all of this together, you have sounded this out. Now you know that B-A-T means bat, so it is bat. So, this is one of the ways of doing this conversion that I was talking about is referred to as grapheme to phoneme conversion. Grapheme is the visual symbol, phoneme is the auditory symbol. So, you have to convert the visual symbol into the auditory symbol in order to understand the meaning of the word. That is the GPC conversion, and when you are reading using the GPC conversion route, you are basically using what is referred to as the assembled phonology route. So, assembled phonology route is basically when you are sounding out each letter sequence in the word and then constructing a sound based representation. However, it is not really straightforward. Suppose for example you are reading a irregular word like pint, P-I-N-T. It is very probable that somebody who has not read this word earlier might make a mistake and read this as pint, because you probably will have more familiarity with the word mint, because mint is something that you kind of come across more often. So, if you come across mint and then you are kind of reading this word pint, you are not really being able to, you will not really be very successful in coming to the correct pronunciation if you are using the assembled phonology route. So, how do you do it? Because the assembled phonology route is leading you to problems. Suppose, and it will lead you to problems in words like bouquet, for example, B-O-U-Q-U-E-E-T. Bouquet basically, you say it as bouquet, but if you go with the assembled phonology route, you will probably say it as bouquet or something like that. Okay. So, it is fairly evident that the assembled phonology route might lead you to certain mistakes. So, what is the solution? There is a solution, and the solution is that some words need to be accessed, some words which are irregular, which are not really following the grapheme to phoneme conversion consistency, they might be accessed directly. You have to memorize them, you have to remember that okay, there is an exception rule being applied here, and this exception rule, the invocation of this exception rule is referred to as the direct orthographic route. So, the direct orthographic route matches the visual code to a lexical entry that is in your brain, and this matching will make the correct pronunciation available to you. You are not going by sounding each sequence of the letters. What you are doing is you are reading this, you know that you know this, you check whether you know this word already, and you come up with a direct pronunciation already. So, also it does not really mean that the assembled phonology route becomes inactive. The assembled phonology route also becomes is active, and sometimes it will lead you to mispronunciations which are referred to as regularization errors. Suppose if I start reading PINT as pint, this is a regularization error. I should remember that this basically PINT stands for pint. and that will be the access through direct route. But sometimes I will make this mistake and read PINT as pint. That is where I am committing the regularization error. Still, the direct route cannot be used for everything, as GPC route generally helps us generate sounds for newly encountered words. Direct route is accessible only for the point that you know this word. If you have not seen this word earlier, if you are not aware of what this word reads like, then you will anyways end up using the grapheme to phoneme conversion, the assembled phonology route, and that is why that route is also very important. This is how the direct dual route cascaded model looks like. You will see that there is a direct connection from orthographic analysis to response buffer, which is the grapheme phoneme rule system, and then there is the orthographic input lexicon and the phonological input lexicon. Again, you will see how these things are connected. More important is, however, I have described already how this model really works. So if you really notice the GPC route, if you look back at this figure, the GPC route postulates serial activation codes for letters. So GPC route basically is going to tell you that you activate first letter first, second letter, and the third letter. This is the serial allocation that needs to happen. So is there any evidence of this? Are we doing it in parallel or are we doing it in serial? So there is some evidence for this. So dual route model basically predicts that there will be larger reading times for irregular words like pint and kernel, etc. And suppose if GPC conversion was happening serially, left to right irregularity in a left to right fashion, irregularity at the beginning of the word should cost more or will cost more than irregularity at the end. And if you really look at the experimental results that are available, you will find that if there is irregularity at the beginning of the word, you generally take more time in reading that word. So it kind of can act as an evidence of saying that this dual route, this assembled phonology thing is happening serially, and it is happening from left to right depending on the direction of text that you are reading. Okay, that is there, but it does not really apply across the board. For some cases, DRC predicts that words with earlier visual uniqueness points, suppose for example the words like dwarf should be read slower than words like carpet. Okay, but this has not really been found. Dwarf is also read as fast as carpet, and then this kind of thing is in a bit of a problem. Again, I am just enumerating some evidence related to what reading experiments have shown, and again this is something that is ongoing. So a lot of evidence are kind of sometimes contradicting. So we talked about how reading would happen, we talked about this model of reading, and this was the dual route model. Let us look at one of the single route models. The single route models, again, it kind of borrows from the parallel distributed processing tradition, McClellan and Rumelhart, and what they say is reading really happens in just one process. What they have is they have a neural network based model, has a particular components, do the orthographic processing wherein the visual analysis is done. It has components that represent meaning, which is the semantic units, and then it has components which have the phonological. So there are orthographic components, meaning related semantic components, and phonology related sound based components. And therein there is this layer of hidden units, and this contribution between hidden units is basically what achieves this process of reading. So if you can look at the figure A here, there is context is also playing a role, meaning is there, orthography and phonology are also interacting. So what happens in this model is, when there is a visual input will lead to activity starting in the orthographic units, which will lead to further activity in the hidden units. Hidden units is where the processing is actually happening, and hidden units is basically where they will convert the visual input into phonological thing. Every word is represented as a pattern of activation across the entire network. How many phonological units are activated, how many orthographic units are activated, how many hidden units need to be employed here. All of this, every word will have an index which will basically give you the number of units activated across the network. Learning to read basically in this kind of a model will involve modifying the weights through experience. So how many words have to be basically read through the direct assembly and direct route, how many words will have to be read through the assembled phonology route. Practice will basically tell this model, practice will basically help this model associate those kind of weights. one processing unit is connected to others, so that one processing unit is activated, it will be able to influence the activation of other units as well. So suppose there is some activation you are seeing in the orthographic unit, because it is connected to hidden units and they are connected to phonological units, there is already some activation there. Because it is connected to the meaning semantic based units, those activations will also go there and the entire network will get activated. To start with, once you start training this network on reading, the connection weights will need to be randomized. There's just some random thing and some input starts and the system starts reading, but with practice, as number of trials pass, the system tries to zero in on the correct pronunciations. So training, up to 150,000, 15,000, 20,000 trials are there. After activation has spread through the entire network, the pattern of activation basically comes out as the output units, and whatever the pattern of activation is there in the output units is compared to what the correct output could be. And this comparison keeps on going on, and the idea is that eventually the network should learn to basically give output the correct pattern of activation in the output units as the correct output is there. So the idea is the network gradually, with practice, with trials, learns to let us say figure out the correct pronunciation of each of these words. Now it seems like a little bit complex, but it is really not. It is one of the very simple architecture of reading, okay, that kind of appropriates human visual word recognition performance as well. Okay, there are ways to look at this model. There is one of the things called phonological error score. Now, the phonological error score is basically just the difference of pronunciation between the correct pronunciation and whatever the pronunciation the model is giving you. So because you compare the correct output with the given output of the system, you kind of come up with a particular score, and the idea is with practice this phonological error score should be reducing, and the correct output and the output that your system gives should kind of be congruent to each other, should match each other. What happens after training? After training has happened, after you have kind of trained the model on 150,000, 250,000 trials, what will happen then? After training, a particular error score, just as I was saying, phonological error score, etc., would basically become lower as compared to the correct output. So the idea is the system is trying to appropriate what the correct performance is. The model will generate lower scores for words that it had learned. Again, I am talking about after training has happened. The model also started producing regularization errors for low frequency words, just as humans would do. So if the humans are basically reading words like brook as book, the model will also start doing that, okay, because it is trying to match the actual performance. Also, it was seen that this model produced longer response times for irregular words because it is difficult to read them using the assembled phonology route. Model started responding to non-word stimuli like people, and it kind of started taking more time to reject words like brain as an invalid word. So after training has happened, these are some of the effects that the model kind of shows. During training, we already saw that you're training this thing on 150 to 150,000 trials. The model is trying to compare the output that it has come up with the correct output, and is trying to figure out whatever the rules are needed, whatever changes are needed, whatever weight adjustments are needed to match the correct output. In that, learning happens, and in that the model learns to read words, so to speak. So we talked about two models of word reading. We talked about the DRC model, dual root model, and we talked about the DRC model or the dual root model, and we talked about the single root model. Now both of these models have also tried to explain how difficulty in reading really comes up. Okay, so both of these models have tried to come up with explanations and explain how some people will suffer from a difficulty to read, referred to as dyslexia. Now you must have all heard about dyslexia at various places. It's been one of the topics of discussion lately. So dyslexia, basically it occurs when a person has a problem in reading, okay, when somebody cannot really read properly, even though they are otherwise intellectually and behaviorally completely normal, their IQ scores are good, their visual analysis is good, everything else is completely fine, just that they are lacking this ability to read. So it's not really a major disorder, really, so to speak. It's not really a debilitating disorder. You might know of various people who've done very well in their lives and have suffered from dyslexia earlier. So the idea is, it is just about making this connection between the visual symbol and the sound symbol, and finally leading to meaning. So approximately 15% of males and 5% of males anyways have suffered or will suffer from developmental dyslexia. Again, this is a data from 1997 from Steen and Walsh, and there are common threads, there are common patterns of difficulties that developed dyslexia and acquired dyslexia have. Now I'll just differentiate between developed dyslexia and acquired dyslexia. Developed dyslexia is something that already happens while the person is maturing. During the growing up years, the child probably is not able to grasp the concepts of phonemic awareness, or some reasons are there, and because of it the child is not able to master reading. That is developed dyslexia. Acquired dyslexia is, suppose say for example some injury has happened, something has happened, and that has led to the difficulty in reading. That could be referred to as acquired dyslexia. So there have been different kinds of patterns that have been common across the kinds of dyslexia that are observed. One of the very important patterns is that there are people who have more trouble reading non-words, like if I write FEEN, feen, than exception words. Suppose the words like have and save and those kind of things. So there are people who have difficulty reading non-words. Also there are groups of both developmental and acquired dyslexics who have less trouble reading non-words, but more than reading exception words. So two kinds of people are there. One who have more trouble reading non-words, less trouble reading exception words, and there are people who have more trouble reading exception words and less trouble reading non-words. So this is sort of a double dissociation that you will see. For double dissociation, it's basically, you can refer to one of the earlier lectures that I've given in the last course, but double dissociation typically tells you that there are two different processes at work in these skills. So when an individual has greater trouble reading non-words and than exception words, they are classified as phonologic or deep dyslexics. If they cannot read non-words, then they are probably having deep dyslexia or phonological dyslexia. The meaning is basically that they are not being able to use the phonological assembly route. When a person has trouble, less trouble reading non-words and they have more trouble reading exception words, then they are referred to as surface dyslexics. The idea is that in surface dyslexics the meaning and the word connection is lost. So they can come up with the assembled phonology route, they can come up with pronunciations, etc. But what has been lost with these people is the connection between the meaning and the sound part. Okay, so the general problem is that they are not being able to connect meaning with the word form that they have activated. It is very important to recognize, however, that most dyslexics will generally form into a mixed category. There will be some aspects of deep dyslexia, some aspects of phonological dyslexia. Okay, so they perform below normal on a variety of reading and reading related tasks, and it's very rare that you will come across a pure phonological dyslexic or a pure surface dyslexic. So both kind of models, as I was saying, basically have tried to explain how dyslexia happens. So considerable research effort has really gone into testing whether these models can reproduce behaviors that dyslexic readers show. Because if these models can really reproduce those behaviors, you can try and mend these models and in the process try and help the people who have dyslexia as well. So according to the dual root theory of visual word processing, there are two ways to come to a word pronunciation. As I have already said, the assembled phonology route and the direct access route. So the dual root model basically suggests that there are two different underlying deficits that give rise to phonological dyslexia and surface dyslexia. Let us look at that. Damage to the assembled phonology route will lead to phonological dyslexia, because the problem here is just coming up with the pronunciations. Because this assembled phonology route is damaged, phonological dyslexia will happen. But these people can read exception words because the direct route is intact here. Okay, so these people basically will not be able to sound out words that are not accessible by the direct route. That is one kind of dyslexia. And on the other hand, if there is damage to the direct route, this would lead to the surface dyslexia, because the link between the word form and the meaning is lost. These people will be compelled to sound out all the words, they will use the assembled phonology root more often, and they will lead to regularization errors like reading pint as pint and not as pint. So these are the two deficits which are leading to two kinds of dyslexia according to the dual root model of reading. Single root models of reading view word reading as resulting from the operation of a unified neural network. So if you remember the parallel model which I was talking about, the single root model has everything linked to each other. So it's, you know, it's not possible that just one of them is lost or something like that, just like the DRC was saying. Okay, so with under this kind of explanatory mechanism, different kinds of impairment result from different types of damage within the same system. Okay, so phonological dyslexia here can be modeled within this framework as a result of damage to the units that are representing the phonological codes. So the phonological units will be damaged. Surface dyslexia can result from changes to other aspects of the model. Suppose some of the hidden units are damaged, or the connection between the hidden units and the meaning units are lost. So again, it is the same system, different aspects of system might be damaged to lead to different kinds of patterns of dyslexia. So while single root models view non-word and exception word reading as being governed by the same sets of representation units running the same processes, different kinds of dyslexia might reflect different underlying deficits, as different kinds of damage to the system will lead to different patterns of behavior. I am not saying there are two different systems, I am saying different patterns of dyslexia are arising because different aspects of this same unified system are damaged. Here I will just show you the reading performance of reading at exception words for both surface dyslexics and phonological dyslexics. You can see that there is the second left, and there is a phonological dyslexic, and then at the end extreme right there is a chronological age match. So we will just try to see how this reading performance can be explained by the two models. Now this figure basically, as I was just mentioning, shows representative data on non-word reading and exception word reading for both surface dyslexics and phonological dyslexics. You can see here that surface dyslexics are more correct at reading exception words. Phonological dyslexics are also slightly more correct in reading exception words, but there is a great mismatch between exception word and non-word reading in phonological dyslexics, and surface and exception word and non-word reading between surface dyslexics. So the DRC model can explain these findings very straightforwardly by proposing that different concepts of the DRC, different roots of the DRC system are damaged in surface and phonological dyslexia. Surface dyslexia basically reflects, again I am just kind of revising whatever I have said. Surface dyslexia represents a problem using the direct root to access word meanings compiled with an intact phonological root. So phonological root is fine, just the link between word meaning and word form is lost. The intact assembled phonology root will enable the surface dyslexics to pronounce regularly spelled words and novel words, but they will not be able to pronounce correctly the exception words. According to the dual root model, deep dyslexia is caused by a problem in the assembled phonology root, which is coupled with an intact direct access root. So here the direct access root is fine, the assembled phonology root is a problem. So exception words these people will be able to read better, but phonological words, I mean the regular words, they will probably have a problem in reading. If the deep dyslexic, that is the phonological dyslexic, has not seen a word before, the assembled phonology root will not be able to compile its pronunciation, and the resulting pronunciation will sometimes be unrelated to the actual pronunciation, because that assembled phonology root is not working. While the DRC model has been used to simulate the dyslexic symptoms, separate lesions have separate damages have in the direct root and the assembled phonology root are necessary to mimic the behavior of surface dyslexics and phonological or deep dyslexics. In single root models, people have also tried to capture how dyslexics perform, and what has been found is, for example, in the original Seidenberg and McClellan model, it could simulate some aspects of poor word reading. And it basically was that when half of the hidden units in the model were removed, the error scores for high frequency words at about the same level as the error scores for low frequency words. So the idea is the number of units are damaged, and that is leading to problems in reading. This reduction in the number of hidden units had a greater effect for irregular rather than regular words, which suggests that a greater number of hidden units is necessary for the model to represent item specific information. More resources are needed for item specific reading to happen. Also, a subsequent model, a different model has been adopted to explain a more complex system of phonological representations, and then it was trained on phonology before it it was kind of trained to read using phonology to recognize words. And when these phonological representations in this model were degraded in different ways, then different patterns of reading difficulty emerged. So, if these phonological units suffered mild damage, then basically the network was limited by, it could not read the representations of different phonemes that differ from each other, different kind of sounds being represented by same letters. When the damage was moderate, from mild to a little bit more moderate, this was basically simulated by eliminating just one component of the phonological system and reducing the number of connections in half in the remaining units on top of the mild form of damage. This kind of damage, in this mild damage condition, the model had no trouble reading for exception words, but it could not read the phonological words. It had mild problems with the reading from the phonological root. When the severe damage was there and most of these phonological units were damaged, then basically what happened was that the severe damage to this network produced deficits in both exception word reading and reading normal words, reading using the assembled phonology route. So, this is one of the ways in which what people have tried to mimic reading of words using these single root computational models. These simulations basically have kind of pointed towards a possible proof for existence of a single root architecture. So, the idea is that these models try and point out and say that it's just that it could be a unified system. The extent of damage to that unified system will lead to different extents of patterns of surface dyslexia and deep dyslexia appearing. So, again, this is something which is going on. I don't really think that this debate is settled, but the idea is that different patterns of word reading deficits that are observed in different kinds of dyslexia might be produced by a computational mechanism that has a single set of connections between the visual input. So, I think this is all from me about reading and dyslexia and word reading. I'll talk to you about something else in the different lecture.